Hello and welcome again to my Physics Online video lecture series. In today's video I'm going to be continuing my discussion of blackbody radiation by discussing what is called Wien's law. This law is basically empirically obtained from Planck's law. In principle you could obtain it by actually taking a blackbody of known temperature, measuring its spectrum, and then finding the basically like peak value, what wavelength it occurs at, and then repeating this over and over and over again for different temperatures. You'll recall from my other video when I was discussing blackbody radiation and Planck's law that I had this plot which for whatever reason is messed up on this machine. It does have a title and it does have axes labels, but they're kind of like dark on dark for some reason. But this plot was done for blackbody radiation at different temperatures. So for example, this blue line right here was, I believe, 2000, 3, 4, 5, and 6. So this is 2000 Kelvin. This one right here is 5000 Kelvin. And this plot is for 6000 Kelvin, which is roughly surface of the sun temperature, for what that's worth. And then you'll also recall that the axes, these spikes along here, these are your wavelengths in nanometers. So this was 500, this was 1000, this was 1500, this one was 2000, etc. These are all in nanometers. The other axis is actually basically your irradiance axis, and it's actually in arbitrary units. So we don't really care what the units are for our purposes here, just they are in some arbitrary units. So what Wien's law basically does is it looks at the peak of these spectra. So let's go ahead and put this again without all the labels on it. And this time I just want to circle kind of where is the peak. So the peak is right here, the peak is right here, the peak is roughly right here. These ones are harder to see because they appear flatter, but they do actually also have peaks to them. Peak is maybe somewhere over here. And you'll notice that if I were to sort of like plot what wavelength are these at versus what temperature were they taken from, that I would get kind of an inverse relationship. So this peak right here, if I were to kind of drop it down a little bit, it occurs somewhere to the left of the peak of the next highest temperature, which in turn occurs to the left of the peak of the next highest temperature, which is to the left of the next highest, which is to the left of the next highest after that. And so Wien's law basically takes these lambda values. What we care about is lambda peak, lambda peak, lambda peak, etc., where this axis right here or this axis right here, these are your lambda axes. So we're looking for the values of the peak as a function of temperature, and we're basically just plotting them, and I'm just sketching the plot here. So lambda peak versus temperature, and what we would find is the lower the temperature, the longer our wavelength is. And so we end up with a plot that basically ends up looking somewhat like this. And the linearization of this is that 1 over lambda peak, or 1 over temperature, whichever you'd like to do. Maybe we'll do lambda peak versus 1 over temperature ends up looking something like this, which is a straight line. And so what Wien's law basically says is that lambda peak is equal to some constant, this is called the Wien's constant, divided by the temperature. So B in this case is Wien's constant. So Wien's constant has an approximate value of 2.898 times 10 to the negative 3 meters dot Kelvin. So this just kind of relates the temperature of the blackbody emitter, so this is your temperature, to the peak wavelength lambda peak, which again is just essentially taking these values of each of the peaks. So I'm just doing this for the green peak right now. And this would be lambda peak for 6,000 Kelvin, because this is the 6,000 Kelvin temperature curve. And doing similarly for each of these. You kind of have to take me at my word that the blue one also has a peak, that the peak is somewhere over here. You can kind of see if you look very closely that, yeah, the blue does rise away from the axis and then it sort of returns to the axis, so that does imply a peak somewhere. Unfortunately, because the temperature is so much lower, the power irradiated is also much lower. You will recall, for what it's worth, that the power irradiated is proportional to the temperature to the fourth power. Specifically, you have your emissivity, you have your Stefan Boltzmann constant, you have the area of the thing that is emitting this radiation, and then you have your temperature to the fourth power. So since this right here is 2,000 versus 6,000, that's a factor of 3 difference in temperature. So power of, we'll call this 2,000 over power of 6,000 Kelvin should look like 2,000 Kelvin divided by 6,000 Kelvin to the fourth power. So this is a third raised to the fourth power. That's 1 over 81. So the green one should have 81 times more power, and thus basically 81 times more area under the green curve compared to this blue one. So for what it's worth, the area under these curves should be proportional to, though not necessarily equal to, the power output. Again, I'm using an arbitrary axis here, so you get a proportionality only. But area of irradiance versus wavelength, irradiance is a function of wavelength versus wavelength, should get you a power. And so this should be about 81 times the area that this one has, hence why it's so much taller. You will recall that these irradiances, so if this is your irradiance axis, along with this being the x-axis being your wavelength axis, that your irradiance is given from Planck's law by 2 times hc squared over lambda to the fifth times 1 over e to the hc over lambda times k sub b t, all minus 1, or where e to the hc over lambda is equal to e raised to the power of the energy of your quanta, which in the context of the Planck's law would actually be a photon energy, and e to the 1 over k sub b t would be e to the power of 1 over E thermal. So this is basically the quantum energy divided by the thermal energy in the exponent. Alright, so Wien's law basically takes this equation and says, where is I at a maximum? For what value of lambda is I at a maximum given some set value of t? Alright, so that's another way of thinking of a similar way, a parallel way of thinking of Wien's law. So I would like to conclude with maybe a simple example or so. So what temperature is needed for a blackbody source to emit a peak wavelength of 560 nanometers? 560 nanometers is very nearly the center of the visible spectrum. So what we use is the fact that if lambda peak is Wien's constant divided by temperature, then temperature is Wien's constant divided by lambda peak. Now, lambda peak does need to be converted to meters given the value that we have for the Wien's constant. So this is 5.60 times 10 to the negative 7 meters. Nanometers is 10 to the negative 9. So we have 2.898 times 10 to the negative 3 meters dot Kelvin divided by 5.60 times 10 to the negative 7 Kelvin. And this gives us an approximate temperature of 5,175 Kelvin. Now, here's a quick double check. Our eyes are adapted to see light centered at whatever wavelength the sun emits. So we said that temperature of the sun, so this is sort of our double check, T sun is about 6,000 Kelvin. That means that lambda peak sun is about 2.898 times 10 to the negative 3 meters dot Kelvin divided by 6 times 10 to the 3 Kelvin. So if I take 2.898 and I divide by 6, I get 4.83. Okay, so lambda peak sun is about 483 nanometers. Somewhat shorter than this center of our vision. And you may ask, okay, so does that match up? Well, yes, because the surface of the sun was an approximation, but also our atmosphere scatters light in such a way that we preferentially see towards shorter wavelengths from our atmosphere than towards longer wavelengths. That's all for today.